For years, a specific image has dominated the briefings of defense analysts: the swarms. Thousands of low-cost, expendable drones and sensors flooding the battle space, overwhelming the billion-dollar platforms of the West through the sheer weight of numbers. The logic was simple: quantity has a quality of its own. If a Chinese-made loitering munition costs 1/50th of a Western missile, the math of attrition belongs to Beijing. But in 2025, during high-intensity flashpoints from the plains of South Asia to the littoral corridors of South America, that math hit a wall of reality. When the Pakistani air defense grid, built almost entirely on the backbone of Chinese-supplied HQ-9s and YLC-8 radars, was put to the test during Operation Sindoor, the screens didn't just show the enemy. In many sectors, they went silent, not because they were hit, but because the systems simply couldn't withstand the friction of a modern, network-centric battlefield. For planners in Washington and Indo-Pacific command centers, this isn't just a win for Western EW, it is the revelation of a structural rot. We've been analyzing China's military-industrial complex as a mirror of the West's. We assumed their military grade meant what ours does. It doesn't. China has successfully exported the disposable economy to the front lines. They've built an arsenal on the logic of consumer electronics, optimized for the showroom, but biologically incapable of surviving the vibration, heat, and electromagnetic chaos of a peer-to-peer war. The problem isn't that Chinese electronics are cheap. The problem is that in modern warfare, they fail first, and they fail exactly when the system can least afford it.
The global defense community has spent a decade obsessing over the cost curve. The logic was simple. If the US and its allies spend $2 million on a single interceptor to down a $20,000 drone, they lose the war of attrition before the first shot is even fired. This fear birthed a fascination with Chinese industrial efficiency. China, the world's factory, seemed uniquely positioned to win a war of mass by simply outproducing the West in the very silicon that drives modern warfare. But efficiency is a double-edged sword. To achieve the staggering volumes of drones and sensors we see in current conflicts, upwards of 4 million units annually by some estimates, Chinese manufacturers have had to make a choice. They didn't just optimize their factories, they optimized the standard of the components themselves. They transitioned from the rigid, expensive, and slow-moving protocols of military spec to the hyper-fast, low-margin world of commercial off-the-shelf, or COTS, electronics. For a consumer in a climate-controlled office in London or New York, a Chinese-made drone is a miracle of engineering. It's sleek, it's fast, and it's remarkably cheap. But for an Indo-Pacific logistics officer, that same drone is a liability waiting to happen. The central contradiction of the Chinese model is now coming to light. They have built a military-industrial complex that excels at sprinting but lacks the structural integrity for a marathon. The question for strategic decision-makers is no longer, can China produce more than us? The question is, what percentage of that mass actually functions after 30 days of salt air corrosion, engine vibration, and high-wattage electronic interference? As it turns out, in the silicon-driven battlespace of 2026, the cheapest way to build a fleet is often the most expensive way to lose a war.
In the sterile environment of a laboratory, a Chinese-made microcontroller and its Western mil-spec counterpart might perform identically. They both process data at the same speed. They both execute the same code. But war is not a laboratory. War is a series of violent physical stressors that begin long before a weapon is ever fired. For NATO logistics officers, the gold standard is MIL Standard 810. This isn't just a checklist, it's a survival mandate. It requires electronics to function from Arctic lows of -65 degrees Celsius to the searing 125 degrees Celsius heat of a propulsion bay. It demands they survive hours of high-frequency vibration, the kind generated by a Humvee on a washboard road, or the rhythmic pounding of a nearby artillery battery. China's commercial first model, however, optimizes for Telcordia, or standard industrial benchmarks. These chips are designed for ground-benign environments, the stable temperature of a data center, or the predictable vibration of a delivery truck. When you take a commercial-grade Chinese drone and subject it to the salt spray of the South China Sea, or the sustained G-forces of a rapid-launch catapult, the silicon begins to drift. Micro-fractures form in the solder joints. The thermal expansion of the plastic packaging deviates from the silicon wafer, leading to delamination. On paper, the unit is still functional. In reality, its mean time between failure, MTBF, has just dropped by 70%.
There is a second, more subtle failure point in the Chinese electronics ecosystem: modular rigidity. Modern Western defense architecture, often criticized for being slow and expensive, is built on the principle of open architecture. Systems are designed to be opened up, debugged, and field repaired. If a specific sensor fails, you swap the module. The Chinese manufacturing incentive structure is the polar opposite. It is built for the integrated black box. To drive down costs and maximize production speed, Chinese manufacturers favor highly integrated proprietary circuits. This is disposable logic, scaled to the level of national defense. During India's Operation Sindoor in 2025, this became a critical failure point for the Pakistani military. When Chinese-supplied radars began showing ghosting or signal lag under Indian electronic pressure, field technicians found they couldn't simply patch the hardware or swap a failing component. The systems were sealed, non-modular, and opaque. For a Western commander, a broken radio is a repair task. For a commander using this black box logic, a broken radio is a supply chain request. This creates a sustainability crisis. In a prolonged conflict, the side that can repair and adapt its electronics in the mud of the front line has a decisive advantage over the side that must wait for a shipment from a factory 1,000 miles away. For allies calculating long-term resilience, the cheap Chinese chip isn't just a component, it's a tether to a manufacturing line that may not be there when the shooting starts.
If physical friction is the hammer, then the electromagnetic spectrum is the invisible fire. In a modern peer-to-peer conflict, the battle space is saturated with high-power microwave, or HPM, and electronic warfare, or EW signals, designed to induce currents directly into an enemy's circuitry. This is where the gap between Western mil-spec and Chinese COTS Plus becomes a chasm. Western mission-critical systems often utilize silicon-on-insulator technology. By adding a thin layer of insulating silicon dioxide between the transistors and the substrate, these chips become inherently rad-hard and electromagnetically resilient. They're designed to withstand the single-event effects of radiation and the high-voltage spikes of an EW pulse that would otherwise latch up or permanently fry a standard chip. China's manufacturing engine, however, is built on bulk CMOS, the same technology found in your smartphone. While this allows for incredible transistor density and low costs, it creates a massive, unshielded surface area for electromagnetic interference. The result is what we call the glass cannon effect. During recent tactical engagements, including the degradation of Chinese-made YLC series radars in contested zones, we've seen these systems fail not because they were hit by missiles, but because they couldn't digest the noise. A non-hardened Chinese chip perceives an EW pulse as a surge of data it can't process, leading to a system-wide latch-up. The hardware isn't just jammed, it is physically compromised. For Indo-Pacific force posture debates, this changes the calculation of mass. If 80% of your sensor net is built on bulk CMOS, a localized high-power microwave burst doesn't just disrupt your vision, it deletes it. For planners in Washington, this confirms a vital strategic assumption. China's numerical superiority in drones and sensors is highly vulnerable to electromagnetic attrition. In the high-stakes game of silicon, the side with the most chips loses to the side whose chips can actually survive the noise.
There is a dangerous seduction in the idea of good enough. The prevailing narrative, the one that fills think tank reports and viral headlines, is that the West is too slow, too expensive, and too obsessed with quality. We are told that we need to be more like China, faster, cheaper, and more comfortable with disposability. But this analysis ignores the strategic reality of attrition. War is not a consumer market. In a consumer market, if your phone fails, you go to the store and buy a new one. The cost is the price of the device. In war, if your drone's guidance chip fails 20 kilometers behind enemy lines because of simple motor vibration, the cost is a lost mission, a compromised unit, and a window of opportunity that may never reopen. The good enough model is a peacetime luxury. It assumes a functioning global supply chain that can replace disposable hardware as fast as it breaks. But in a true high-intensity conflict, that supply chain is the first thing to be targeted. When the replaceability model meets a blockade or a surge in manufacturing interdiction, the side relying on disposable electronics finds itself with a fleet that is failing from the inside out and no way to replenish it. My stance is this: we are not witnessing the triumph of Chinese mass. We are witnessing a systemic gamble. China has bet that the next war will be a sprint, a short, sharp shock where volume overwhelms quality. But if that war turns into a marathon, as almost every major conflict in the last century has, the structural fragility of Chinese electronics will shift from a manufacturing efficiency to a national security catastrophe.
The revelation of 2025, from the silent screens of Caracas to the 88-hour air war of Operation Sindoor, is that mass is a deceptive metric. For decades, we've measured military power by counting airframes, hulls, and missiles. But in a conflict defined by the electromagnetic spectrum, we have to start talking about quality-adjusted mass. If China produces 1,000 PL-15E missiles, but those missiles have a 60% terminal failure rate when facing modern Western or Indian electronic countermeasures, as was documented during the engagements over the Punjab, then China doesn't actually have 1,000 missiles. They have 400. The non-obvious strategic insight is this: the Chinese industrial base has built a peacetime arsenal. It is an arsenal designed for the appearance of parity. By utilizing high-volume commercial silicon and integrated black box architectures, they have achieved the look and feel of a world-class military at a fraction of the price. But war is the ultimate auditor. When the friction of combat begins, when the vibration of the carrier deck, the salt of the sea, and the invisible fire of EW hit those circuits, the disposable economy collapses. For Indo-Pacific force posture, this means the US and its allies don't need to match China drone for drone or chip for chip. They need to match China's effective mass. If a single, hardened, mil-spec Western platform can survive and operate in an environment that fries 100 commercial-grade Chinese units, the cost curve flips. The West isn't being outproduced, it is being out-quantified by a system that hasn't accounted for its own fragility. The future of deterrence in the Pacific won't be won by the side that can manufacture the most chips. It will be won by the side that can manufacture mid-tier resilience, systems that are cheap enough to lose, but durable enough to actually show up to the fight.
We are entering an era where the most important component in a weapon system isn't the explosive, it's the solder joint. As the global supply chain for high-end silicon continues to bifurcate, we have to ask ourselves, are we valuing the speed of production over the certainty of performance? For the planners in Washington and the strategists in Tokyo, the lesson is clear. Mass without durability is just expensive target practice. If you found this strategic breakdown valuable, consider what happens to the global balance of power when the world's factory realizes its products can't survive the very war they were built for. What is the true price of good enough? I'll leave you to reflect on that.